thank you. So greetings from Northern Germany. My name is Kobus, and you might hear that I'm suffering from cold symptoms today. So I'm even more pleased that I'm able to present our results on variability from my office at home. And I thank the organizers for that opportunity. And I hope that you can understand me well anyway. Okay, so can I go to the next screen? Yeah. Many pre-main sequence stars show temporal brightness variations, as we heard, for example, due to changes in the accretion rate. And in contrast to measuring variations in the total brightness distribution by using high-resolution interferometric observations, we can study variations in the brightness distribution of protoplanetary disks. And one example are these beautiful pioneer images of HD 50138, which show a morphological change of the brightness distribution of the disk. With the different near and mid-infrared instruments at the VLTI, we are able to trace the dust in the upper layers of the innermost region of protoplanetary disks, where at the same time the resolution is sufficient to spatially resolve a disk region which is comparable to the size of our solar system. And the VLTI has now been in operation for nearly 2 decades, so the archive is really a treasure chest containing multi-epoch observations which cover timescales comparable to orbital motion of structures located at a few astronomical units in the disks. Now, the big question is, do these available multi-epoch observations contain evidence of temporal variability? So let's take a look at the observations we included in our study. So basically, we searched for pre-main sequence stars for which observations in at least 2 nights have been obtained. And we found in the VLTI MIDI Atlas 51 objects. And besides that, near infrared observations with Ember and Pioneer for 16 and 33 objects respectively, so that we have in total observations of 68 pre-main sequence stars. For the comparison of the observations, we focus on the visibilities, but these depend not only on the potential time-dependent brightness distribution, but also on the observational setup. So we are limited to visibilities which have been measured using equal baselines. One example I show here on the left-hand side. So we have visibilities measured in 2014, which are significantly smaller than the visibility which has been measured with the same baseline in 2012, which indicates that this brightness distribution has changed, where the disk structure appeared more complex in 2012. To quantitatively compare the visibilities which have been measured with different spectral resolutions, we averaged them over the wavelengths. And then I plotted the visibility differences against the time delay between the respective observations, where at the top we have the absolute deviation and at the bottom we have the significance. And we can see that for a time lag of about 800 days, we have significant variations of more than 3 sigma, indicating changes of the brightness distribution. On this slide, I have summarized all objects for which pioneer observations, which are directly comparable, are available. And yeah, of these 7 objects, 4 show significant deviations and thus indications for temporal variability. And just for orientation, at the bottom top, we have this object, which is the one from the previous slide. And we have HD 50138, which was the one from my first slide with the nice pioneer images showing the change of the asymmetric brightness distribution. Here we have the same plots for the Ember observations. And of these 5 objects, all show significant variations and thus indications for temporal variability, where these first 3 objects we just saw pioneer observations, which also indicated temporal variability. So for these, we have evidence of temporal variability both in H and K band. Unfortunately, we cannot say anything about the N band, as the available media observations do not fulfill our criterion for the baseline similarity. So to summarize the current status, from the available multi-epoch observations, we compared Pioneer and Ember data of 9 objects, and thereof 6 show evidence of temporal variability. But one question that remains is, can we learn something about variability from the remaining observations? And indeed, we have found one strategy that allows us to analyze these data despite the mismatched UV coverage, where the idea is that we have to estimate the impact of the baseline deviation so that in any measured visibility differences, we can distinguish between the impact of the deviating baselines and a potential impact of temporal variability. So in this approach, we extend our comparison to observations with moderate baseline deviations up to 10%, and we plot the differences of the measured visibilities over the relative baseline deviation. And for this object, we see very large deviations, slightly more than 0.5. But it is not clear whether these deviations are actually caused by temporal variations or whether they are solely caused by the deviating baselines tracing a very complex brightness distribution. So to find out, we have to estimate the impact of the deviating baselines. And for this purpose, we compared visibility or visibilities measured within a very short time interval of one night in which we do not expect significant variations. And we can see that these visibility differences are typically smaller. So the differences of the visibilities measured with a larger time lapse of at least 22 days are much larger, which indicates that these additional deviations are caused by temporal variations of the brightness distribution. Yeah, we applied this approach to analyze Pioneer and Ember observations of a total of 20 pre-main sequence stars, which meet the requirements to be analyzed with this method. And we find evidence of temporal variability in 6 objects, which I listed here. So in most cases, we just confirm temporal variability that we just found in the direct comparison of visibilities measured with equal baselines. But we also find evidence of variability in 3 additional cases, which I highlighted here in yellow. If we now put the results of both approaches together, we found evidence of temporal variability for a total of 7 pre-main sequence stars. And the very interesting question that now arises is, what causes the found variations? Unfortunately, the temporal coverage of the observations is not sufficient to say anything about the periodicity of the variations. However, what we can do is to classify the variations based on their phenomenology. And in principle, there are 2 apparently different types. On the one hand, we have symmetric variations, for example, in the case of a change of the star to disk flux ratio. So if this ratio decreases, the brightness distribution appears more extended in each direction, and thus the measured visibilities decrease independent of the chosen position angle of the baseline. On the other hand, there are asymmetric variations, for example, in the case of the orbital motion of a structure in the disk. And in this case, the visibilities both increase and decrease depending on the orientation of the baseline with respect to the orientation of the asymmetric structure. To investigate the symmetry of the variations, we now plot all visibility differences we identified as being caused by temporal variability over the position angle. And for this object, we see that on the shortest time scales, the variations seem to be symmetrical, where on the largest time scale of a bit more than 2 years, we have deviations in both directions, so increasing and decreasing visibilities. So here, the movement of a structure in the brightness distribution is a possible cause for the variations. Besides, for this object, we find also asymmetric variations for HD 50128. You remember this one? It was the one with the Pioneer images, and which was not surprising for 2 known binaries. And with that, I would like to summarize. So we analyzed Pioneer and Amber observations of in total 21 pre-main sequence stars, whereof 7 show evidence of temporal variability. And by classifying the variations based on their symmetry, we found indications that in some cases, the variations might be caused by changes of the asymmetric structure of the brightness distributions. And studying these in more detail would be very interesting, but requires observations with sufficient UV coverage, as you already heard, which would be possible with the Jara array. With that, I would like to thank you and would be happy to take any questions.
Thank you very much, Julia, for the talk. Do we have any questions in the room or online? One here.
So about the object you mentioned many times, HD 50. So you detected variability in with Pioneer, right? So did you see also variability in Matisse data?
So far, I did not, or I do not have any Matisse data for that. But yes, you're right. That would be very, very interesting. Yes.
Okay, thank you.
Is there any other questions? There's one.
Sorry, yeah, it's because she's full screen.
Yeah, there's one online. So with the use of spectrointerferometers, do you plan to explore other aspects of the visibility curves variability, i.e. the change of chromatic slope that could trace structural changes?
Okay, I heard part of it. It is on the chromatic change, if we can learn something from that for the variability. Is that right?
Sorry, is that again? You can read it in chat, full question.
Yeah. Yeah, okay, so yeah, having a look at chromatic changes would of course be very interesting because yeah, it is much more sensitive or much more, yeah, it's more sensitive to changes because we are not we do not have to measure absolute values, but we can just compare the chromatic changes, and with that we can learn something about the dust properties and how they change in the disk. I think yes, that would be very interesting.
Thank you. Comrade, if you had a question.
Yes, so from these indications that there's a movement of asymmetric structures, so do you think these structures are long-lived enough, like a clump going around, that you could actually really go and do now observations to actually do a complete image now and then at a later stage to really trace that? Are they long-lived enough for that?
I cannot say because we have not the temporal coverage to really see whether we see changes on different time scales, but just from the orbital skates, I just would guess that having a look in different episodes, periods, we have a chance to see the movements of these structures also in future observations.
So these would be prime targets for follow-up.
Yes, of course, yeah.
Okay, thanks.
And Corinne, if you had a question.
Yes, thank you, Julia, for your talk. AK-SCO is known to be a binary. So do you have a look to the closer phases that you measure with Pioneer on this object?
Okay, 2 things on that. So we decided to include the known binaries in our sample because they are great targets to see that our method is working. So if we find variability for a known binary, that's good. And the second thing is I had a look at the closure. I had a short look at the closure phases so far. And for all these objects where we found these asymmetric variations, indeed the closure phases are non-zero. So I think that would be the next step to have a deeper look at the closure phases, yes.
Thank you.
Okay, thank you. Are there any other questions? Okay, in which case, can we thank Julia again for the talk?